by dr. Now dx by dr is the relation.
Yeah, okay, I mean...
And dt by dy plus dt by dy, dy by dr plus dt by dz. So from that you will figure out how basically you transfer the function.
Yeah, okay, that helps.
So covariant, I figured out right now. I mean, I kind of had this idea, but so I think we should write it down. I will write down there. So contravariant is ds remains same. And transformation of components of ds length. And covariant is transformation of function itself, how the function will look like in the new coordinate system. I should write it down.
It's funny that, in learning something like this, you can memorize every formula and someone asks you to work it, you can work it, but you may still not really realize what you're doing, And realizing what you're doing is more difficult than... Actually realizing what you're doing is more difficult.
It is actually just both these are basic this thing, that chain rule. But what it means, that's what, it's difficult to... These guys, they write a lot of formulas, but I think the really who do physics, they don't write it because maybe they know already or they don't feel it. I don't know why. They don't really mention it in any book, like what's happening. They just say contravariant, covariant. I think they have read the same books and then they just write the same thing. I don't know.
Yeah, I think so. Or maybe they tried to come up with a good conceptual explanation and found it was difficult. And so they say, well, here's the definition. I mean, that's kind of a way out. It's an easy way. If you're having a hard time describing conceptually, you say, well, I just define it like this.
That's what even Einstein said, right? That if you can't explain it simply enough, then you haven't understood it.
Yeah.
So this is contravariant, covariant. And this dt by all these will come up as a matrix. Like these are like three equations, right?
Yeah, the transformation.
Those will come as a matrix. Okay. A contravariant vector, they gave just an example, spatial velocity was one example of contravariant vector, dx by dt, dy by dt, dz by dt. We want to transform that from Cartesian to spherical. Then what will you do? Like you just transform it using the rules. And contravariant vector. And then a contravariant vector is tangent vector to a parametrized curve in space-time.
Makes sense.
So v beta is dx beta lambda equal to dx So generally, if it lambda is like tau,
Yeah.
then it becomes total derivative because it's not a partial anymore. If the parameter of the curve is lambda using coordinate system, the tangent vector. Yeah. So they have the four velocity vector is like what we saw already, dt by d tau and dx by d tau, where tau is a parameter along the curve world line of the particle. So proper time. Now one form, consider a scalar field phi is a scalar function of x beta is invariant in the Lorentz transform. Gradient of a scalar field in coordinate system is given by, it's the same thing. Definition of a one form, like if you consider a scalar field, so basically it acts on scalar field. If there is a phi, like if there is a function, it's like a field you can consider. That's why one form is mostly on fields. Because
so the one form would be, well, the one form would be the gradient of the field. Yeah.
So that's why. So they said that let's take an example of velocity for contravariant. What actually they meant is, I think, why they took that example, which they should have explained.
Yeah, velocity is okay. I mean,
Because it's dx dy dt, basically.
Yeah.
Dx dy dz.
Yeah.
Then you have, because it's like a length.
Yeah.
So velocity will be just d by dt. So you can have like velocity and vx, vy, vz, and you transform it. It's basically the same. And field they transform using one forms because, as you saw, because it's a gradient. Because actually, there's nothing to write. So as we saw,
just the gradient of phi would be a
because it's like a equation,
Yeah.
like it's like a function,
Yeah.
and transform it, you use one forms. And so generally, if you have four things, then there will be a 4x4 transformation matrix for like D. There will be a 4x4 matrix here, which will relate it to this is a 4x4 matrix, and it relates the two V alpha so VL, this is a contravariant, and like this length thing will be, components will be transformed to this, and using this, and this is a 4x4 matrix because this will go from 0 to 3 and this will go from 0 to 3. We'll have like those components. And for one form, this is still. And for one form also there is a 4x4 matrix, and that will look like V prime alpha equal to Dx beta dy prime alpha d beta. This will also be a 4x4 matrix. So this will be a function, and how it will look like in different coordinates. Okay, so now tensors.
Now, one point about this, the way he's doing it at least, when you create this matrix for a vector or one form, when you use it, I'm pretty sure you need to follow the column and row. He's using like a column and row convention.
He's saying
Yeah, the vector is going to be a column and the one form is going to be a row. And when you use that matrix on a one form, you better multiply the row times the matrix, I think. Because if you try and multiply it out as a, if you try to use the, if you don't use a row for the one form, you won't get the right answer, I don't think.
So you are saying this is a column?
That's a row. That's a column.
This is
That's a column.
And this is a column.
And that's a column. But the one form, yeah, right.
So when you have to, when you multiply this into this plus.
Yeah. So that's the obvious way. But the one form has to be a row times a column. So VB has to be a row. Yeah. So that's not gonna that won't work. The row has to come first.
Oh yeah, sorry.
Yeah. So that threw me for a minute before I realized what was happening there.
Yeah, this into this plus.
Yeah. So if somebody, so I suspect that this is one of the things that can get a little bit confusing when you go between different books, because he's using this row and column convention where the dual is a row, and I use that. I mean, that you use that in quantum theory all the time. Which I think is the only reason I noticed it happening. But I think in some other books I've seen, they don't use this kind of convention. And they would actually end up with a different, if they were going to make everything into a column, they would end up with a slightly different matrix.
Okay.
So that's just
But
something
I
to
think
be
it
careful.
convention.
Something to be careful. That's the kind of convention that can be very confusing if you just run into a different book and things look different. Yeah.
But I think it just, you can use, stick to one convention.
Yeah, I like the row column convention because I'm used to it from quantum theory.
Yeah, but I think the only conceptual thing to take out of all this is that what we saw here.
Yeah.
The only conceptual. The rest all is just details, how to calculate and what are the conventions. But another thing I don't understand is, like, I couldn't figure it out is if it's a, if you will see that in tensors. Okay, so next is tensors. So as long as we are dealing with the sort of differentiable coordinate transformation we have discussed so far, the laws of physics must be invariant, a principle known as general covariance. And in plain English, this means the mathematical laws of physics must be the same irrespective of the coordinate systems we are using. The fundamental importance of tensors, because transformation properties of tensor components are basis independent. Basis independent, yeah. If a tensor equation is true in one coordinate system, it will be true in all coordinate systems. As there are no preferred coordinate systems in general relativity, it makes sense to use tensor equations to formulate the theory. So now they are saying, like, this 0, 0 is a scalar, like any number is a scalar. And if there is a tensor and this is rank 0, 0 is scalar.
Yeah.
This is contravariant. This is covariant.
Yeah.
And as you said, this will be column. This will be B alpha A, B, C, D. And this will be X beta equal to E, F, G, H.
Yeah.
So he said that if you have a tensor alpha beta, it will be V alpha to X beta. It will be like A, E, A, F, A, G, A, H, and whatever. And you multiply this to basically.
Yeah. So the only thing that now here's what happens. That one works. So that's a column times a row, which I think of as an outer product, which gives you a matrix. Now the only issue here with this row column business is I think sometimes he goes, I'm not sure about this, but I think if he wrote it like this, you should get the same thing.
Yeah.
But if you strictly follow the row column convention, you'll get a column times a row. Now you
Yeah,
get a
you
column
will.
times a row. You'll get an inner product. But I'm not sure
No,
if you
row times a column.
Yeah, row time. Yeah, now you'll get a row times a column, and now you'll just get a scalar inner product. So I'm not really sure if he follows that or not. Maybe he does.
Follow what?
That I mean,
That a contrast element has to come first.
would he give? Would this be? Would this give a? You know, would this give an inner product? Would this give a scalar? You know, if we're following this convention, that should give us, you know, EA plus FB, you know, that should give us a scalar, right?
But what does it mean here?
Well, this, okay, so this one, I mean, this is good. This is just a matrix.
No, I
That
mean if
works.
you write it as x beta v alpha, then is it still this?
Well, not if he really follows the row column convention, right? Because then it would be,
No, how will you write it? It will be written the same way, right?
oh no, it would just be a scalar.
Uh,
Because, you know, this is going to be E, F, G, H, column times a row, right? A, B, C, D.
yeah, I was also thinking about it.
Yeah.
But I think maybe we should see what it means to multiply these two. Like what is this? What is like this is a component and this is how the function behaves, right? So it's like this is like d by dx, this is dx.
Yeah, well, here's the thing. So, I mean, there's two different pictures here, right? There's the component picture, and there's the row and column picture. So, the component picture would have these two things. Maybe, you know, maybe it just strictly depends on what you put on the left-hand side of the equal sign, right? Because if you put this on the left, like, so if you strictly, because usually people just go by the component picture, I think. I mean, he's putting these rows and columns in there, which I kind of like, but usually it seems like we're just talking components. And if we're talking components, then it's obvious that these are the same thing, right?
No, I'm asking you, they're the same things. We should see, right?
Yeah.
Because this will be a vector. This is like a gradient. Like it depends. Like this will be like dx, and this will be like d by dx. And when you write like this, it will be d by dx. If you are trying to differentiate something, here you will be different. Here you will have the differentiation done here. You will have some
Yeah.
function, and then you will multiply, I think. But here you will differentiate that vector itself, and that's why you will come up with a scalar, I think. So these two will be different, I think, because these are not like he's representing it.
So you're saying, okay, because this.
So because this is a function. This is how
Because that's actually a function.
Yeah.
Oh, that's a good point. Okay, so even if you treat them as components, they'll be different because that's a function.
yeah. I think these two will be different because
Because. So really, this is.
or maybe it won't be.
Well, I'm not sure. I guess that's interesting. So you think of this, then this is a number.
Hmm.
This component is a number, but this component is a function, an operator.
Yeah. It's an operator, I think, right?
Oh, I haven't thought of that before. Okay, so a one form is an operator.
Yeah. So
So is that true? Is that true?
it's not an operator, but
Well, I mean, if maybe
yeah,
it
it's
is.
operator
Yeah,
actually.
yeah. I mean, that's an operator. So, I mean, is that generally true? A component of a vector is a number, but a component of a one form is an operator. Can we say
Component of
that
a-
that's true?
component of vector is a what? Sorry.
So a component of a vector is a number, and it might be an infinitesimal, but it's a number, and a component of a one form is an operator.
Component of one. Yeah.
So can we say that's generally
I think
true?
it's true, yeah. So here
that's news. I mean, I didn't think of that before. That's a new thought to me.
because what will happen here is I think that's why you have so many components because it will just be this function multiplied by this. That's why. But here you will have this function which will operate on it. It can potentially operate on this. You can get a different thing. So that's why we'll have to look at some examples.
Okay, that's a lot. So that's something to think about. This is new. This is a new thought to me. I haven't figured this out before. Someone should say that. It doesn't say that anywhere.
Yeah.
If that's true.
Yeah, that's the problem with most of the books.
Oh, this
But
is good.
I haven't looked at quantum mechanics. What's the difference if the operator is here or here?
Well, okay, so in quantum mechanics, I mean, when you're dealing in quantum theory, these rows and columns, it's something different. The duals, okay, you know, you have bras and kets. You've seen these things, right? And that's a column and that's a row. But none of these are operators. These are just numbers in here. Okay, so you know, so that's an inner product. That's an outer product. But so this is always just going to be a scalar. This is going to be a matrix. And you know, this is an operator. A matrix is not. The matrices are operators. There. So that's. So things are different. I mean, you're describing. This is, you know, like in quantum information. You know, a qubit is just a column vector with two complex components. This is. I could do this, but we probably shouldn't do this while we're doing this.
I just looked at it in a different, like the way we are looking. No, the thing I was asking is if the operator is in quantum or in any mathematical theory, if the operator is here, because if you, for example, the operator is this, right? So this into del and del into this is a very different.
It's very different. Yeah.
So if you look here, it's B E. If you B F B G B H, and then C D E E C D F F C D G G C D H H. So actually, if you, for example, say this is del, so this will be d by dx, d by dy, d by dz, d by d whatever s. So here, what you're doing is, if you see here, it's E throughout, F throughout.
Yeah.
G. So here you are just taking that operator, you are multiplying it by the component.
Yeah, it's very easy to multiply a number times an operator.
Yeah.
But it's not so easy to multiply. I mean.
No, that's what I'm saying. When you reverse it out, it will be a scalar, because when you reverse it out, it will be like, as you said, it will be E F G H and A B C D, right? So you are saying it will be like E A plus F B plus G C plus D H, right? So if you now again substitute this, it will be like d by dx, d by dy, d by dz, and then you are operating on this. For example, a is some function x square, b is something y. You are operating on that, and you will get some
very different.
Yeah, and as opposed to this, where you have this, where you have del. So you have this, and you have this 4 alpha over from 0 to 3.
Here you end up, it's still a matrix of operators.
Yeah.
And,
yeah, exactly.
Yeah.
But
so
now you're operating.
Now you're operating. Yeah. Wow. Okay, I have to really think about this, because this is.
That's what I thought.
You know, if this is true, I mean, if this is true, the difference between the numbers and operators, or it could be functions and operators, someone should write this in big bold letters. You know.
Yeah. So the way they will write it is, I think, dx, d by, or whatever, x, d by dx, as compared to d by dx, x square.
Yeah.
But they won't tell you explicitly, that's the problem. But my question was, this is okay. Like, he wrote this, even in this book he wrote this. But I was thinking, if this is this, it will
That's a problem.
look at same as like T alpha beta, but it's not actually. Like, this will, how will you write this? So my conclusion was, maybe you need a first contravariant for this tensor to be true.
Yeah,
That's
it
what it looks
seems
like.
it
You can't
seems
have
like you do.
one form.
Yeah, okay, yeah, it seems like it. Yeah, you know, that's funny because I have actually sat in a class where a guy said these are just components, so it doesn't matter the order. And I'm like, okay, but I was just thinking of them as numbers. I think that he might have been wrong.
I think you, yeah.
I was in a
I don't know.
no wonder I'm confused.
But actually, when they write like this, G nu, G nu V G alpha beta, but these are two, that is, and as opposed to G alpha nu, for example, or nu A, as opposed to nu A G or something like that.
But
They
now-
come up with same thing.
I wonder, is it always true, okay, is it always true, this distinction between like functions and operators? Because what about when, maybe I'm getting ahead of things, but what about when you know, right? I mean, did I change it into an operator?
When you have alpha, so let's look at this, right? That's what I do basically. Generally. This is beta, and this will be like, you are saying this is alpha. So this, for alpha, for example, 0 to 3,
Yeah.
0 to 3, 0 to 3, 0 to 3. And you're saying, what you're saying is,
I mean, because I can lower the index by doing this, right?
but I think, so you're saying, yeah, you converted this into an operator, right? Like this was a vector. So this is just a del. Now you have 2 down, right? So this will be del square. This will be, right? This is alpha beta. It's not just beta. When you had beta, you wrote del. So that is d by dx. Now you have d square by dx square, right? And this is like some function. So you operate it out in once, then twice. So when you, for example, if this was say x raised to 4, right? And this is like a when alpha beta are same, say x square. So this will be like, first you differentiate, it will be 4x cube. Again you differentiate 12x square. You come up with this like function, like from this function, or like this component, you differentiated it twice and came up with this one form. Like what is one form? What is differentiation? Is gradient, right? You twice differentiated it. So basically, if there is a curve, you differentiated it, you got a tangent, right? But like you got some function here, some function here. That will give another curve of how the function, it's like acceleration, for example. So now you got another curve. So like when you differentiated, you got a gradient. You got a gradient of that curve itself. So you are asking me, what did you transform it to, right? Like this was length, like this was some a vector.
Some vector,
Yeah. And you converted, you are saying, did we convert it to a operator? That's what your question was, right? So for example, if it's V0, beta is 0, so alpha will go, so it will be, I think we should write it down to see what's happening, right? Let's write it down. So if, for example, if V is 0, so it will be V0 equal to 0, 0, V0 plus G 1, 0, V0 V1 plus G 2, 0, V2 plus G 3, 0, V3. So now V0, V1, V2, V3 are all in those directions, right? The way you can look at it is V0, V1, V2, V3 are vectors in those directions in that coordinate system. And what is G0, G1, 0? These are just components of those metrical system. So this will tell you, Yeah, this is the.
Let's suppose that was just a velocity vector.
This was velocity.
Yeah, and that was just, let's suppose G was just the Minkowski metric.
Then
We'll just get a negative, we'll just get a, what, a negative,
negative V0. No, but what is a metric? That's the question, right? Like here, you are saying this is a tensor of, like, you are multiplying these two things. This is, you are using a metric tensor. You are using the contraction properties to convert. That's what you are saying, asking, right?
yeah.
This is, the question here was the operator and does it matter, and this is a tensor. So this was a vector, this was a one form. Here you have a vector, and you are saying when I operate on the vector with a metric tensor, I am getting one form.
I'm getting a one form. But that one form I get doesn't seem to be an operator.
I mean, this won't be operator, but that's what I think. Like this VB will be like V0. This is V0, right? There will be a V1, there will be a V2, there will be a V3. So like V beta is not just V0, it's V3, V3. That is an operator. Like V beta will have this V3, V2, V1, V0, which will be an operator. So V beta, you can use this to operate on something. Like it will be.
So you're saying even it may not look to me like an operator, it may not be a differential operator, but it will still be something I can use to operate nonetheless.
It can be a differentiable operator as well. I mean, we don't know. It can be a different. I mean, you can differentiate this operator as well, right? One more time, right? I think you can say gamma and add gamma here or whatever. I don't know.
Okay, well, there's a lot to think about here.
No, but I think this is right.
Yeah, that's right. Yeah,
but here I think how you should look at it is, this is a, for example, you said velocity, right?
Yeah.
This is a velocity. Let's consider it as a length, that invariant transform, x, y, length, actual length,
okay.
vector.
Okay, so just a length.
Length
all right.
vector. And now your
So just a position vector.
position vector.
Yeah, okay.
So now you multiplied by a metric tensor. So this means that what are you doing? Like these are you will differentiate it by alpha beta. So when you will have, for example, if you say alpha beta is 0, both are 0. What will this be? This will be acceleration, right?
Well, but it depends on the metric. But I mean, if I'm just
no, it will be like, for example, this, right? These are all 0, right, in flat space. And now you said that this is position.
Yeah. So
sorry, not this one. Let's say V1, and here also it's V1. It will take the same form. Like,
yeah.
But when it beta is 1, it won't take the same form actually.
So the lower index position will just have the negative time, right? The lower index, V lower index, will just have the negative of the time.
Yeah, when this is 0.
Yeah.
But you should not think of it as just a negative time. What I'm saying is, what is actually happening is 2 times differentiation with respect to time. Like if you consider this as CT, even if you consider this as CT, like a distance parameter, you are twice differentiating with time, which will give you a acceleration. Like this 0, 0 is like TT. And when it's on the lower side, as we saw, it's like differentiation, right? Like this is like a del square when it's on the lower side, when it's one form.
Well, I mean, that's what I'm wondering. I'm wondering if it's always like that.
Yeah. When it's lower, so that's why like G alpha beta and G alpha beta, you multiply, you get identity matrix, right? They're inverse of each other. So this will have a form of like this, But if you
Yeah.
look at this, it will be 1 upon r
Oh, no,
square.
right.
So it's
Yeah.
like meter minus square.
Yeah.
So what does that tell us? We can look at that. When it's in the upper, when it's the contravariant, it's like it's r square, right? That means it's dx into dx, right?
Yeah.
Sort of. But when it's lower, it's 1 upon r square, like it's like 1 upon d by dx, because it becomes 1 upon r square. It's like delta x are multiplied into.
Oh, I see what you're saying. Okay. All right.
Because in this example, they mentioned that d30 is v3x0, which is dE. d30 is v3x0, which is dE.
I feel that behind these transformation rules and these tensor manipulation rules, where the rules are fairly simple, but behind these rules is a more complex picture.
Yeah.